Okay, thank you for your introduction. Hello, everyone. It's good to see you again. I'm Dewen Zhou from Nanjing Tech University and Ghent University as well. Actually, I'm a joint PhD. My topic today is the crack propagation behavior in P92 welded joint based on crystal plasticity and combined with its film. I'm going to introduce my research in the following 4 parts. So the cracks in a welded joint, I believe that there has a planting investigation, which is based on an experiment, but there's a very limited numerical investigation because it's very difficult to do the crack simulation, which is also interacted with the microstructure. Here, first, our CPFE model is established according to the optical micrograph of each line in a welded joint. And we calculated the average grain diameter. So our model is the representative of the real materials. And then we conducted some tensile tests for our third steps to identify the materials. And then we proposed the parameter optimization procedures, which will automatically identify the parameters for each microdesign, and the comparisons between the simulation and experiments are shown here. And we all know that the welded joint of P92 is working in the power plant, which is the working temperature is more than 650 degrees. So the creep problem is very important. So, but actually, the traditional constitutive model with the AF Pauling model cannot capture the creep deformation during the stress welding as shown here. So that's why we modify this, and we can see the modified model can capture the creep deformation very well. And then I'm going to introduce some depth parameter, that is the fatigue indicate parameter, namely accumulated plastic strain and the energy dissipation. These two FIPs are widely used in the CPFE simulation for the fatigue problems. But these two FIPs cannot capture the creep deformation, creep damage. So we propose the net slip, which is a description for the dislocation slipping. And if you are interested in this work, you can refer to our previous work here. So we also extracted the 3 damage parameter evolution during this loading cycle. And we can see during the dewelding process, there's no increment for the first 2 parameters, so they can't capture the creep deformation. And this picture shows the stress relaxation during the dewelding. According to the 6th picture, we can see that our proposed model and damage parameter is very effective. So this slide shows the crack propagation criterion used in our research. The cracks is introduced by the X-film. So we have to make sure the 2 things. The one is the critical value for the damage, which means when the damage meets the critical value, the crack will initiate, and the subsequent damage propagation slip activity will contribute to the crack propagation. And the crack propagation direction is defined by choosing to be along with the slip plane with the most damage ahead of the crack tip. Here, the damage parameter could be anything like the shear strain, energy dissipation. Here, we use the net slip, and it can be the other FIPs. So no matter what kind of damage you use, it's always related to the slip plane. So we call this criterion as the crystallographic criterion, which is shown illustrated by these figures. And you can see the yellow plane is the slip plane with the highest damage, and the intersection line between the slip plane with the model plane is the crack propagation direction, which is shown by the red arrow. During our simulation, we find some wrong results, which we can see that the crack will propagate back. Suppose there will be a 3 cracks at the edge or the surface, and we apply the tensile load on the other side, on the 2 sides. So we know the crack will propagate to the other side. So there's no definitely no any chance for the crack to propagate back. So this is incorrect. So how will this happen? You could see there are some limitations which is recorded in the above documentation, and I will show here. One is the enriched element cannot be intersected by more than one crack. As you can see here, this black line is like the black line, and this arrow is the predicted crack propagation direction. And in this element, the predicted direction is shown by this intersection line. So we already know that it's gonna propagate along the red line. So if it is so there will be two crack lines in the element E0. So this is not allowed by the X-beam. So it has to propagate along the black line, which results to the wrong direction growth path. So for this situation, when we detected this situation, we will keep the propagation direction unchanged, or should I say keeps at the previous one, and then it will when it's propagate to the other element, you will have the right path. So this modification only microscopically change the path, like in one or two elements, but for macroscopic view, the propagation path is not changed. And the other two situation is that the crack is not allowed to turn more than 90 degrees in a single increment. As you can see here, the angle between the previous and the new crack lines is larger than 90 degrees. So somehow, we don't know, somehow the optics will give a wrong direction, just indicated by the blue one. So when this situation happens, we will specify a new crack propagation to make sure that the angle between these two lines is less than 90 degrees. And you can see the modification between crack propagation path between and after the modification here. So in our research, we can introduce 4 pre-cracks defined according to the original position. It can be defined as type 1, type 2, and type 3, type 4 cracks. And I also listed the notation of all the 12 slip systems for the PCC crystals. And here's the results for under the low circle fatigue. As you can see, for type 2 and type 4 cracking, at the very beginning, where we see a tortuous pulse, which can be defined as the short crack propagation region, which is really closely related to the dislocation activities. After that, we will see a nearly a straight line at a certain angle to the loading direction. And this region, we will find the rapid cracking. So I take this region as the long crack growth region, which is independent with the dislocation activities. And we can notice that between the short crack pulse and long crack pulse, there will be a retardation. And there will also be a near obvious retardation for crack 1, which will be introduced in the next slides. For type 1 and type 2 cracking, we will notice there's the intergranular cracking, which means the crack will grows along the green boundaries. And we also know that for type 1 cracking, there will be an obvious retardation. This is because there might be a very sharp turning, which is the deflection is more than very close to 90 degrees. And second reason is the very hot neighboring greens, which can be seen by the Smith factors. All these greens have very small Smith factors. Because the orientation in our model is randomly set, and the microstructure follows the real experiment one. So our simulation results, our model is representative. We just want to know, is there any specific slip system that will be activated for the crack propagation? So we recorded and all the activated slip system for the crack propagation along the crack growth path. And we can see that for the type 4, even when we increase the string amplitude or under the other loading conditions, the cracks shows the periphery growth on this 2 slip system, and we conclude that the possibility for the cracks to propagate along the two slip system is as high as like more than 67%. So when we increase the string amplitude, we can see that the crack propagation rate is also increased. And there also will be two regime. The first is short crack regime, and then the long crack propagation regime. And the angle is like 45 degrees and 51 degrees to the loading circle. And we also see that for the type 3 cracking, there will be a very straight line that is very close to 45-degree angle. And you can see this figure, each colors represents a different orientation. And you can also see the green is how the green is plotted in our model. And we can see the slip system activated for the crack propagation is different. The orientation is different. The activated slip system is also different, but the crack path is nearly a straight line. That's why we call it the long crack propagation regime, which is it's never independent on the dislocation slipping, but also will be affected by the external nodes. This slide shows the results under safe crepe fatigue interaction loadings. As we can see, there are an obvious retardation from here, and here for type 1, type 3, and type 2 cracking. All the retardation can be found at the green boundaries. That's why because the green boundaries is really an obstacle for the crack propagation. Okay, here's our conclusions. We can see that the type 4 cracks tend to grow along these two systems. And when we increase the string amplitude, the crack propagation rate will also be increased. And our model can capture the short crack features and the long crack propagation features. And during the transition, there will be a retardation. Thank you for your attention.